not for enzymes. So let's look at an illustration of that. So in this illustration on the left, we have an imaginary box, and this box is full of golf balls, and some of the golf balls will spontaneously turn from that grayish, whitish color to the color brown, and they will only do this at a certain rate. And so if you have all these golf balls and you allow them to turn colors at their natural speed, then a small percentage of them are going to have changed to brown after an entire year. If you compare this with the number of golf balls that are going to change color in the presence of an enzyme, over the span of a single second, you actually have all of the golf balls changing color in that single second just because of the enzyme assisting them in changing from the original color to the brown color. So this is a dramatic example of how much an enzyme can increase the speed of reaction. So that means that so many more molecules can undergo reaction if an enzyme is present. So on the right side here, we have a couple of enzymes, or some enzymes, and the time period in which the reaction would occur once without the enzyme, and how quickly the reaction will occur with the enzyme. So for this one at the top, OMP decarboxylase, this is an enzyme. Without this enzyme, this reaction would only occur once every more than 10 million years. So this reaction would not occur frequently at all. It would not occur within, organisms could not rely on this reaction because it would simply not occur frequently enough within their lifetimes. However, with the enzyme catalyzing this reaction, we have it occurring multiple times a second. And the same goes for all of these other enzymes. And we see that there's a huge difference in the rate of reaction, or the number of times it happens per unit time, with the enzyme, which is the catalyzed number here, the catalyzed value, and without the enzyme, which is the uncatalyzed value here. So we go from the order of over 1 million years down to a little less than a second for uncatalyzed reactions. And this last one isn't that slow, but still using the enzyme is even faster. It's on the order of 1 millisecond. And so that's why we need enzymes in our cells, because they speed everything up so that cells can respond more quickly, and they could react to the environment, they could make products more quickly, etc. Now this next slide, that we saw in the beginning, shows a reaction where glucose and fructose are bound to one another to make sucrose. Now we know that some organisms can make sucrose, but when we look at the delta G value, we see that it is positive. The delta G is Gibbs free energy, which is a measure of the energy that either has to go into or comes out of a reaction. Positive delta Gs mean that energy needs to be put into the system in order for the reaction to go forward, and that means that it's an unfavorable reaction. So even though we know that organisms make sucrose in certain circumstances, this is an unfavorable reaction. So how do organisms provide this amount of energy in order to make sucrose? Well, that's kind of a trick question, because they don't do it in this way. just as if you didn't know how cars worked, you might think, oh man, how do people push these giant vehicles to where they want to go? Well, that's not how it works, right? We don't push cars. We put gasoline in the car and burn the gasoline, or we use electricity or whatever. And so, similarly, cells can get around this energy barrier by having workarounds, basically. They have different pathways that get to the same point in the end. So here we see coupled reactions where we start out with glucose and add ATP, or we have glucose and ATP, and we add a phosphate group from the ATP to the glucose. Now, if you don't remember what ATP is, you should go and take a look at the structure of that molecule. It is a nucleotide with 3 phosphate groups, adenosine triphosphate, and it's relatively favorable. It's relatively easy to remove one of those phosphate groups. And so this is a favorable reaction to remove a phosphate group from ATP and add it to glucose. Now we have glucose 1P. That was a favorable reaction, and so that can go forward in the cell. That's not the end point where we want to end up, but we could continue with this product, glucose 1P, and now we could remove the phosphate from glucose 1P, which is also favorable because phosphate is still a good leaving group. And using that energy, we can add the fructose to the glucose and form that bond, making sucrose in the end, which was our target product. And now we've done this in a favorable series of reactions rather than using a single reaction, which would have been unfavorable. So the takeaway here is that there are many steps in these pathways that we're going to be talking about, and the number of steps are necessary to kind of work around and make a system that is as favorable as possible. So we use the least amount of energy necessary, and we always generate energy if possible instead of using energy. Also, I want to point out here, and you'll see this in all of the pathways that we talk about as well, the products for one reaction here at the top are going to be the substrates or the reactants for the next reaction here. And so that leads us to this awesome network graph where we see that metabolic pathways are linked. And so all of these different colors are different types of metabolic pathways, but if you look close enough, they're all connected in some way or another. You could see that there's an orange line here, and so this is some chemical, and this chemical can be bound by this purple dot here, which is an enzyme, and so it could go into the purple pathway, which is, I believe, it might be carbohydrate metabolism, but it came from a completely different pathway. And let's pick another one here. So energy metabolism, that's pink, and so we see that energy metabolism can connect with other pathways. And again, let's take a look at the node here. So this is an enzyme that can both bind to whatever this pink product is, or a pink chemical, and then it can also bind to, or it looks like it needs to be reacted in the presence of this chemical that is in this amino acid metabolism pathway. So you don't need to know how to read this kind of chart. You just should know the takeaway here, which is that many different pathways and series of reactions are linked in the cell, and the products or the substrates and their concentrations are going to affect other pathways in the cell and the cell's ability to carry out certain reactions.